Now that we've talked about how to find the area, surface area, perimeter, and volume of different objects, it's important to understand how these final equations or solutions, what they tell us about scaling. Meaning, if I double one of these length scales, how does it affect the changes here? If I double it here, does it double or does it quadruple? Understanding how to identify it is really important because then you can see, all right, if the property depends on surface area, let's say, and you understand the scaling effect of changing one of these length scales, then you can essentially tune that property by changing that length scale, knowing how it changes and affects your surface area. So take a look at this. This should be a relatively short video, just going over how to think through this scaling effect. So first we can think about area and perimeter. So for 2D objects, so we can look at a rectangle, a square, triangle, and circle. And we have our perimeters already defined, our areas defined. So let's think about this from a scaling perspective. So first let's look at the rectangle. If I have a height defined here and width defined here, we know the perimeter, right? The length around this rectangle is just 2 times the height plus width, right? Because the height showed up twice, the width showed up twice. We know the area is just height times width. So if I double both the height and the width, then I know my perimeter is going to double, right? If this is 2h and this is 2w, total is just going to double, right? I can pull that 2 times out. It's just double my original perimeter. If I do that if I double the height and the width, again, there'll be 2h times 2w, it'll be 4hw, so it's 4 times the original area, right? So you can see that effect. Similarly for a square, if my length scale is L, if I double the length component, then the perimeter is going to double, right? So 4 times 2L is going to be 8L. That's twice as much as 4L. 2L squared is going to be 4L, so it's 4 times, 4L squared, so that'll be 4 times L squared, the original area, right? Now, if you just look at the rectangle and just increase the length scale or double just the height, let's say, then the area would just double. If you do that, if you try to compare it to the perimeter, it's a little more complicated because there's a additional component. So it's not going to double or quadruple, it's going to add a certain component to it. So when we think about scaling, it's a lot easier to think about scaling when we have, or we can ignore the additional component. When we have to account for it, is not a straight like multiplication type of contribution, right? So there's an additional piece that you have to look at. So we're not going to look at that for this video. Then we have a triangle. We can look at it as individual length scales. We can look at it as the height component. Remember, the height is defined as one of the points, and you draw a perpendicular line to the opposite side, right? And then we could define the perimeter just adding up all 3 sides, or if we have one of the heights and b is my base, then this would be just 1/2 base times height. And if I double, let's say a, b, and c, each of these lengths, then I get that the perimeter is going to double. That's pretty obvious, right? If you double all the lengths, it's going to double. If you double the height and the base, then your area is going to go 4 times. Now you can ask the same question. If I double a, b, and c, how does that affect my area term? Well, then you would have to define the relationship between a, b, and c to your height term, and you can solve for that, right? So there's other ways, depending on what you're actually interested in, you can back these things up. Circle. For the circle, we have 2 pi r for the circumference or perimeter, and pi r squared for the area. And if I double my radius, we can see that the perimeter or circumference doubles, and then we can see the radius is squared, so that increases 4 times. This is similar idea as like the square, right? We have a squared relationship, and so just changing one length scale automatically, if you double that one's length scale, you automatically increase the area by 4 times and not just 2 times because there's a square relationship. Whereas in these cases, there's multiple length components. So if you only double one of them, the area is only going to double. But if you double both of them, as we can see here, we increase the area 4 times. So let's take a look now at 3D objects and how we affect surface area and volume. Now we can take a look at 5 different 3D objects to look at the effect of changing one length scale and how it affects the surface area and volume. All right, so we'll look at a cylinder, a rectangular prism, triangular prism, a sphere, and a cone. You notice that in the surface area section, I've split up when there's multiple surface areas. Like the cylinder, there's a top and bottom surface. That are just the circles. I split that up and split that from the side surface. Now the reason for that is because if we're just adding all these terms, we're not going to be able to easily compare for a lot of these terms how something doubling makes a direct effect. Again, because of that additional component. If it's just multiplication, then it's easy to see that relationship. And then we have the volume as well. All right, so first we'll look at the cylinder. And if I double the radius, we can see that the volume is r squared. So 2r is going to be turned to 4r squared. And that means that the volume increases 4 times. And then we can see that the side surface, right, the surface right here, that surface area will double, right? Because we can see 2 pi r times L. So r doubles, then the side surface area doubles. If we were looking at top and bottom, those are just circles. So we know if the radius doubles, because there's the r squared relationship again, the top and bottom surface areas will quadruple. Then we have a rectangular prism. We split the front, back, left, right, and top, bottom. And then, so we can see that if we double the length scale, the volume will just double, right? So if we just double one of the length scales, just the L value. And then we see that two sets of these surface areas are affected by length, right? Left, right, top, bottom, but the front and back walls don't have that length scale as part of the surface area at all, so it won't have any effect. But the other ones that do have an effect, it's just HL or WL, so those would be doubled as well. Then we have our triangular prism. So we have 3 sets of surface areas, right? So the bottom base, that rectangle, the left, right rectangles, and then the front, back triangles. And so if we double the length scale L here, we can see that we double the left, right surface, those rectangles, and then the bottom base rectangle we also double, but the triangle itself doesn't change. All right, similar to what we saw for the rectangular prism. And then similar again, the doubling the length scale L will double the volume. Okay, for a sphere, if we double the radius R, then we can see the surface area has a square relationship. So that will be increased 4 times or quadrupled. And then we can see for the volume, since we have a cubic relationship, this will be 8 times, increase 8 times. And then finally, for the cone, we can see that if we double the radius, the bottom circular surface area will double, or sorry, because it's r squared relationship, will quadruple, so 4 times. And then the volume, because it is a square relationship, will also quadruple, right? So recognizing what's the relationship will help. Recognizing like something like, if we look at the cone, if r doubles, then this one is not as easy to say how much it increases, right? So it's going to increase, the amount it increases actually depends on what the original height is So that needs to be taken into account when you look at these things. But things like volume and area of a specific surface, it's a lot easier to look at.